Good morning, everyone. My name is Dr. Leah-Nani Alconcel, and I am an Associate Professor of Space Engineering in the School of Metallurgy and Materials at the University of Birmingham. And I'm here to talk to you, well, I'm not there, I'm really sorry I'm not there, but I'm here to talk to you about materials in space. So this slide is a summary of many things that I've worked on over the course of my career. So that's me down in the bottom left at the Jet Propulsion Lab in Mission Control. And these spacecraft that you can see in all the pictures are things that I've worked on over the course of my career. So Cluster is in the upper left, Cassini is in the upper right, and JUICE is down the bottom here. And this is some students of mine doing some environmental testing at RAL Space in Harwell in the UK. So I'm going to give you a few examples of materials in space and how they are used. So I'm going to start with my first example, which is JUICE, the one that you saw on the bottom of the last slide. So what is JUICE? JUICE is a mission to Jupiter. It will be the first ever spacecraft to orbit one of Jupiter's Galilean moons. And the Galilean moons of Jupiter are Io, Europa, Ganymede, and Callisto. So JUICE will go into orbit around Ganymede in over a decade from now. So why would we go to Ganymede? What is interesting about Ganymede? So what makes Ganymede interesting is the combination of things that help to support life. So if we look at the Earth, we've got liquid water, a stable environment, essential elements, and chemical energy. And Ganymede has most of these. It might have the chemical energy, we're not sure yet, which is part of the reason why we have to go there. And the other one I've highlighted is Europa, which is, if you remember me saying, is another one of Jupiter's Galilean moons. It has all of these things. Water, stable environment, essential elements, and chemical energy. However, it is also much closer to Jupiter. And one of the things that means is that it's got a much harsher radiation environment. And a harsher radiation environment means a much more expensive spacecraft in order to study it. So that's why we've chosen to go to Ganymede. So what does Ganymede look like on the inside? This is what we think Ganymede looks like on the inside. So there's the icy crust, and then underneath that is a layer of liquid water, which is the liquid ocean. Then there's another layer of ice through which we get heat from the core of the moon. And the core of the moon, so we know that Ganymede has an intrinsic magnetic field, just like the Earth. And so what that means is that the middle of the moon is liquid metal, which means it's rotating around and being very, very hot. And so it heats up the rock around it, and some of that heat gets into the ice, and that's what helps to form the ocean. What we don't know is how thick this ocean is, or how close to the surface of the crust it is, or if it's in contact with the rock underneath it. We're not sure. And one of the things that we're hoping to discover with the JUICE spacecraft is which of these conditions we have. So, for sending a spacecraft that far away, we have to make sure it can function really, really well. So the spacecraft has to provide power. So you can either use solar panels or nuclear power. JUICE is solar powered. You have to have some way of controlling the orientation of the spacecraft, which way it's facing, and you do that with chemical engines. You also need, and this is where the choice of materials becomes really key, radiation and heat shielding. You need some way to talk to the Earth because you have to send your information back. So you need an antenna, and that's the dish on the front here. You need a central data storage system, which is shown here. And you need stable platforms for the payload instruments, so vault and boom. So the vault is the spacecraft body itself, and then an example of a boom is down here on the bottom right. So one of the really, really important materials on JUICE is the thermal blankets, and those are the shiny bits that you can see in the picture here. So this is the structural thermal model that was first built of JUICE, and it's just the body of the spacecraft. And then you can see it's wrapped in the shiny stuff, and that is what is called multi-layer insulation, or MLI. So multi-layer insulation is all over the spacecraft. It's not just on the body of the spacecraft, it's on everything else. So that's what these pictures show. These pictures show a little section of a boom with a sensor on it. So this is part of one of the payload instruments that makes measurements. And you can see it's got a little black hat. And so this is all the MLI that's wrapped around this instrument to protect it and to keep the temperature stable. And then the shiny gold stuff is on the cable that connects the boom and the instrument to the spacecraft. So if you want to test this stuff and make sure that it actually works and is controlling the temperature inside the sensor and inside the boom, you use a thermal chamber like this one. So you can see it's got these black shrouds, and you can seal it up on one side, and then it's got a bright light that shines in and illuminates part of the MLI, and that's what the sun simulator beam bit means. So one part of the boom is getting really, really hot, and one part of it is staying in shadow and staying really, really cold, just like it would in space. So then what you do is you do what's called a thermal cycling test. And so a thermal cycling test can take place over a very long period of time. If you test the whole spacecraft, generally you do it over months, but this is only a very small piece of the spacecraft, so it was thought sufficient to test it for about a week. So that's on the x-axis here. You can see the timeline. This is a number of hours, and then the temperature of the chamber you can see over on the y-axis. So you can see that first of all, you heat up the chamber and make it really warm, and then you drop the temperature by putting in liquid nitrogen. You make it really cold, and then you turn the sun on, and the sun makes some bits of the chamber really, really hot, and other bits of it stay reasonably cold. And those are the bits that are protected from the that are in the shadow. So you can see that the MLI out on the outside is experiencing extreme temperatures of hot and cold. So after a week of this being subjected to extreme hot and cold, we checked the sensors that were being protected by the MLI and found that they were still intact. Okay, another material that's really important on JUICE is called solder. So solder connects electronics components to the boards that connect them to the central data unit of the spacecraft. So it's part of the brain of the spacecraft, if you like. So this is an example of some old analog electronic components. So we've got resistors, capacitors, diodes, and transistors here. And that's what these little diagrams mean, if you've ever seen a diagram of an electronic circuit. So in the olden times, these would be the ones that were attached to the boards. But these days, we use what are called surface mount devices. So they don't have those legs on them, and they don't go through the board. They're just mounted on top of it, kind of stuck on top with the solder. And these are the same sets of components, so resistor, capacitor, diode, and transistor. And what you can see is that there's a real difference between an old analog board. So this is the board for the magnetometer that flew on board Cassini, which went to Saturn. And you can see all these big chunky electronics with their legs, and they've got these through-hole attachments, so they're very securely connected to the board. Whereas these ones, these surface mount devices, are stuck to the board just with the solder. So what does this mean? When you're using an analog component, you've got a really strong mechanical joint between the component and the board. And with a surface mount device, suddenly there's nothing holding the component to the board but the solder. And the solder suddenly becomes a really critical material. It was before, but it's even more so now. And part of the issue with solder is that you can only use certain types of it, otherwise the joints can fracture. So these pictures show examples where the solder joint has been underfilled, so not enough solder is there, and you can see these cracks have formed in them. And what that means is the component could possibly fall off because it's not connected to so there's not just that there's an electrical problem, there's also a mechanical one. The component could fall off the board. So space solders, there's a very limited number of them that we can use, and they all contain lead. Now we very rarely see leaded solder used in ground-based applications anymore. And the reason for this is that tin whiskers, which is this long pointy thing you can see here in the middle of this microscope image, tin whiskers can form in the absence of gravity and extremely low temperatures. And it's really difficult to create a material that has the same stability as lead-containing solders at very low temperatures and without gravity. So the space qualification of these, of lead-free solders, is really complicated and is taking a really long time. So we still have a lot of work to do in order to find the best and the most sustainable materials to use in space. Now, we did manage it with JUICE, and so I want to play you a little movie about how JUICE was launched. I think I might have to swap back to my, turn off the laser pointer and get the mouse back. There we go.
6, 5, 4, 3, 2, 1, top. Allumage Vulcain. Allumage AP, décollage. La propulsion est nominale. La propulsion est nominale.
In Kourou, there are many places from which to watch these launches. As you can see, the beach, any place. And here we have a glimpse again of the rocket. Raphael, it's an amazing sensation for you as well, I'm sure.
Yeah, even with the clouds, it's just...
La trajectoire est nominale, tous les paramètres bord sont nominaux.
It's really, really always impressive, and it's an emotion to see it.
So, as you can see, that launch was really recent. When will we actually get to Jupiter? So we've launched in 2023. It's going to take the spacecraft 8 years to get from Earth to Jupiter. And after it gets to Jupiter, it takes a little while to go into orbit around Jupiter. That's what JOI, Jupiter Orbit Insertion, means. And then it's going to have to transfer to its orbit around Ganymede. So it will go into circular orbits around Ganymede between 2033 and 2035. And 2035 is the nominal mission end. Now, I've said nominal because quite a lot of missions that get sent to the outer planets get extended quite a few times if the payload is still working, because there's very few spacecraft that have ever been to the outer solar system and stayed there. So here's a little bit more about the journey to Jupiter. So part of the reason why it takes so long to get out there is that the spacecraft has to do a number of flybys of planets of the inner solar system. And the reason why it does this is it helps out it gets gravity assists every time it flies by one of the inner planets. And so Jupiter helps to push it, the flybys will help to push it, make it go faster as it gets out, as it travels toward Jupiter. So it's going to be controlled by mission controllers at ESA, and I hope this is obvious, but once you've made your materials choices on the ground, you cannot change them once you've gotten into space. So we're relying on our materials that we've chosen before launch in order to make sure that the spacecraft can survive from 2023 through 2035. So hopefully, if this all goes well, what we should find is that we are able to make measurements as we go into orbit around Ganymede that will help us to understand how deep this ocean is, whether or not it's touching the rock, and how long. Infer some things about how long the ocean has been there, and if it has been there for a long time and it's been stable for a long time, then there's the possibility that these oceans could support life. Now, JUICE won't be able to determine whether or not there actually is life there, but it does give us a good benchmark for understanding habitable worlds around gas giants. And there are lots and lots of those in our galaxy, and we know that already. So there's potential for the development, if we can demonstrate that Ganymede has a really stable subsurface ocean, we can demonstrate that there's indeed a possibility that life could evolve in many places around our galaxy, and indeed the rest of the universe. Now, so my final point is that without a really deep understanding of the materials that we can use in order to build these spacecraft, you can see the cuddly MLI blanket here around JUICE, and we would not be able to do any of this exciting space travel. So I hope that gives you a flavor for the use of materials in space and why they're so important. And I hope you enjoy the rest of the session. Thank you very much. Bye.